Hello, I hope that you're having a good day. Um, Today I'm gonna be going through the physics waves and sound test review sheet. Um, this will be helpful if you're trying to prepare for a test or the exam, and you just want to get a little bit of extra practice or just confirm what you already know. Oops. Um, so let's just get into it. Okay, a wave moving on a string has wavelength lambda and frequency 2f. A second wave in the string has double the wavelength and travels at the same velocity was the frequency of the second wave with respect to the first wave. Okay, so we know its wavelength and we know its frequency. So for the first wave, right? The second wave, it has the same velocity, okay, which is pretty key here. But it has double the wavelength, and whenever you double the wavelength and the velocities are the same, the frequency will half. So we're going to have half of the original frequency, which is 2f, which is just f. This makes sense. Like whenever you double or triple, quadruple the wavelength, the frequency will half, third, fourth. It's that inverse relationship. Um, Why can astronauts talk to each other inside the International Space Station normally, but need radios in their helmets to converse outside of the station? This is because sound requires a medium to travel, but outside the station, there's no medium. Okay, so how does changing the temperature of air affect the velocity of sound in the air? It's pretty simple. Increasing the temperature will increase the velocity, and decreasing the temperature, I apologize for my handwriting, will decrease the velocity. So it's just a direct relationship. For each, whoa, wait. Oh, I'm sorry, I don't know how that happened. For each increase of 1 degree Celsius, the velocity will increase by about 0.6 meters per second, and the same goes in the opposite direction. Number 4. What do ultrasonic and infrasonic describe? Okay, so these are terms that are based on what humans can hear. And ultrasonic is going to be greater than 20,000 hertz, but any infrasonic sounds will be less than 20 hertz. So these are basically just ultrasonic and infrasonic sounds, or sounds that are based on what humans are able to hear. And any ultrasonic sounds can be greater than 20,000 hertz, infrasonic less than 20 hertz. That makes sense. Okay, so we don't need to worry about these. These are crossed out. The material will not be covered in the test or the exam or quiz or whatever. So number 6, how can we produce beats between two sounds? To, to produce beats between two sounds, you just need to have two frequencies that will be close together. So have two frequencies with or two have two sounds with close frequencies, but not equal. Can't be equal, but they need to be close. All right. For constructive interference, the waves need to be in phase. Okay. So like crest, lines. I'm just going to type this. The crests line up. And troughs line up. And just to help, I'm going to draw a sketch of what this might look like. So let's say you have two waves. It would be like this, and then this. And then you add them together, and then what you get is something like this. Notice how it's a bit higher up. It's more, its amplitude has doubled because you add them together, and they, instead of canceling out, they'll kind of add on to each other, if that makes sense. Meanwhile, destructive interference, they're out of phase. So this means basically opposite troughs and crests, if that's a way that makes sense to put it. So I'm kind of running out of room. Let me just erase this. So two waves that are going to produce destructive interference will look something like this, right? See how they're out of phase. So when you add these together, what you should get is something that's either like this, or it's has much less amplitude because they kind of cancel each other out. Cancel out. Okay, number 8. When the speed of a wave is constant, how does increasing the wavelength affect the frequency? So by the wave equation, V equals F times lambda, which is the wavelength. If this has to stay the same, right, and the wavelength increases, this means that this has to decrease in order for the velocity to stay the same. So decrease, I'll type that, frequency decreases. Alright, which harmonics can be played by open pipes? Well, not much I can explain here. Open pipes can play all harmonics, so n equals 1, 2, 3, so on and so forth. Meanwhile, closed pipes can only play odd harmonics, so n would be 1, 3, 5, 7, 9, so on. Okay. If the fundamental frequency on open and closed pipe is 50 hertz, so that's your first harmonic. What are the next two frequencies that both instruments can play? So let's make a table. I think it'd be kind of useful to do. Harmonic number. Open, closed. So when you have a harmonic number of 1, 2, you only need to go to the second one. Or no, 3 actually, because the next one that the closed pipe can play is 3. Because closed pipes can only play odd harmonics. Okay, so we know this one's going to be 50 hertz for both, right? And there's nothing for the closed pipe for 2 hertz because it cannot play an even harmonic. But for the open, the next would be 100 hertz, which is the answer for the open. We don't need to worry about this. It would be 150. And for the closed, it would also be 150 hertz. So our answer would be 100 hertz for the open and 150 hertz for the closed. Okay. Hopefully that makes sense. Identifying wave properties. Identify wavelength on the diagram. So wavelength is going to be, you could do crest to crest, top to top, or you could do trough to trough, which would be bottom to the bottom, or you could do, one of these midline points to midline points. You can't do this. This would be half of a wavelength because it needs to repeat that full behavior. It's coming down here, so when it starts the next wavelength, it also has to be coming down in order to repeat that behavior. So I'm going to identify this. That's a wavelength. An amplitude. Amplitude is going to be midline to your trough. Your crest, or midline to your trough. Do either one. This is going to be your amplitude. What type of wave is showing? This is a transverse wave. Transverse wave. Okay, two examples of two types of transverse and two types of longitudinal. Okay, transverse. Two examples would be light. Pretty much any electromagnetic radiation. Another one would be radio waves. Longitudinal. Well, the obvious one is going to be sound. That is the big one. But another would be earthquake. Earthquake waves. They go back and forth. I guess the best way I can describe it. Like the vibrations. Okay, so that's number 12. Number 13 we skip. How would the wave speed of a 500 hertz tuning fork compare to the 250 hertz tuning fork in 23 degrees Celsius air? Now, something that might trip you up is you might think, okay, it's half of the frequency, so that means that the wave speed is probably half, right? But no, the wave speed, it's in practice, even though velocity is equal to the frequency times the wavelength, the velocity is not going to change if you change the frequency. Instead, if you change the frequency, the wavelength is just going to increase. Okay? The only thing that the wave speed depends on is the temperature and the properties of the medium. So, if it is in the same air and is in the same temperature, it will not change. Okay? That's very important to remember. It only depends on the temperature and properties of the medium. Okay. Almost done. Or like we're halfway through. A wave is observed crashing to shore every 6 seconds. What's the period and frequency of the wave? Alright, the frequency given, it crashes once every 6 seconds. So, one time per 6 seconds. Because your frequency is going to have like something happening. How often? How many seconds? So seconds will be a denominator. So that would be just, you could say 1/6 hertz, or excuse me, or about 0.167 hertz. And the period, that it's how long it takes for each time for it to occur, would be 6 seconds. So period be 6 seconds. Okay. Waves transmit. They only transmit energy. They do not transmit matter. Yeah. So it's not going to be matter. It's not going to be energy and matter because it's only energy. um, Frequency. So if something is higher frequency, it's gonna be higher pitch. Lower frequency, lower pitch. All right, so let's draw two waves. Wave number one, I have like this, and then ooh, maybe I should give myself a little more space. So this is wave number one. Just a quick little sketch. And this is wave number two. Okay, which would be higher pitch? So you can see, all right, how about let's have this one be like that. Okay, so wave here, wave number two would be higher pitched because as you can see, it has a higher frequency. It's happening more often. It cycles more often, which means that it's going to have a higher pitch because frequency, the same thing as pitch. Meanwhile, wave one has a much larger frequency. Much lower frequency. It has a longer wavelength, so it's going to be lower pitched. All right, just a couple more problems. A certain type of microwave radiation has a frequency of 3 times 10 to the 6 hertz. If the speed of all electromagnetic radiation, which includes microwaves, is 3 times 10 to the 8 meters per second, what is the wavelength in meters of this wave? All right, so we're given the frequency here, and we're given the speed. You want to know what's the wavelength. Here we're going to use the wave equation, which is V equals F times lambda. Okay, so this means that lambda is our velocity over our frequency, which is going to be 3 times 10 to the 8 meters per second over 3 times 10 to the 6 meters per second. Those 3's will cancel, and in the end you'll be left with, or wait, this is, 1 second, that is supposed to be seconds, or no, it's supposed to be hertz, sorry. So what you're going to be left with is 10 to the 2, because you subtract those exponents since you're dividing. 10 squared meters, because in meters, which is just going to be 100 meters. So that is answer for number one. Number two, Alexandra is standing 110 meters from the face of a tall cliff. She claps her hands and hears an echo 2.20 seconds later. What's the temperature of the air? Alright. So, we're given our distance. Okay. So, we know that our velocity is going to be our distance over time. But here, because the sound, it has to travel from Alexandra to the wall and back to her, and she hears that in 2.20 seconds, as travel double the distance of 110 meters. So really, it's doing a total of 220 meters. So we're going to have 220 meters up here, because it's double, over 2.20 seconds. Okay, so that's just going to be, I believe that would just be 100. Yeah, it's just going to be 100 meters per second. Okay, so we know the velocity, but why would I need to know that? Well, the reason you need to know that is because there's another formula for velocity that can let you find the temperature. That is velocity 331.4 plus 0.6 times temp. Okay, so we already know our velocity. So let's just plug that in. 100 equals 331.4 plus 0.6 temp. So minus 331.4 for both sides. I really need room. I'm just gonna move it. I'm gonna bring some of the room, some of the work down here, but I'm gonna erase it later. So you get negative 231.4 yeah, equals 0.6 times your temp divided by 0.6. You get temp is equal to, let me plug that into a calculator, negative 231.4 divided by 0.6. I get negative 386 degrees Celsius, because that is in degrees Celsius. Okay. Let me just write this up here. Negative 386 degrees C. But I'm gonna have to get rid of this work, so. Okay. If you blow across the mouth of an empty soda bottle, closed tube, that is 0.22 meters deep, what is the lowest frequency in hertz you expect to hear if the column has an air temperature, if the column of air has a temperature of 20 degrees Celsius? Alright, so there's two formulas you're going to need to know here. The first one is that the frequency of the nth harmonic is equal to n. This is for closed pipes or closed tubes. Is equal to n times v over 4 times the length. Okay, because we know it's a closed tube because it's a bottle. Okay, and then our other formula is going to be our velocity is equal to 331.4 plus 0.6 times your temperature. Okay, so let's calculate our we need to calculate our velocity in order to plug this into the formula, because we know our length, and because it's asking for the lowest frequency, this is going to be n equals 1, that first harmonic. So we'll know our length, we'll know our velocity, and we'll know our n by that point. But first we need to plug it into this formula. Okay, so velocity is going to be 331.4 plus 0.6 times our temperature of 20 degrees Celsius. If I just plug that into my calculator real quick, I get 331.4 plus 0.6 times 20. I get 343.4 meters per second. Ooh, that'll be our velocity. Okay. Now we need to know what our frequency would be. So F1, because it's our first harmonic, our lowest frequency we can hear, it's going to be 1 times our velocity, which is 343.4 over 4 times our length, 0.22, which is going to be, if I plug this into my calculator, 1 times 343.4 divided by 4 times 0.22, I get 390 hertz would be our frequency, because your frequency is always in hertz. Alright. So what if it was in a 0.22 meter straw instead? Okay, so we have, the cool thing here is that we identify we have the same length, we have the same temperature, we're assuming, which would mean the same velocity, and we're asking in this scenario for the same harmonic frequency, right? But the only difference is it's an open tube. So we don't need to plug and chug again, because we have pretty much everything the same, except for we're changing from a closed tube to an open tube. So since over here, let me just write out the formula. For open tubes, it's going to be, or open pipes, whatever, it's going to be NV over 2L. Okay, so here it's over 4L, over here it's over 2L. So this one is going to be 1/2 of this, right? And this one is going to be 2 times the other one, right? So we know this frequency. We just take 390 times 2, and that will give us 780 hertz, because it will just be double based on the formula, since it's over 2 instead of 4, right? So you don't need to use the whole formula and just plug all the numbers in again, since you already did that. It's way easier just to identify that we're just changing the formula a little bit, and we're not changing all the numbers, right? So number 4 produces 7 beats a second when sounded with a 350 hertz tuning fork, and 8 beats a second with a 365 hertz tuning fork. We're asking what the frequency of the string is, okay? So we know, let's call our frequency here F, okay? So we know that we have 7 beats. That'll be in hertz. I'm not going to write the units here. We're going to use our formula. Absolute is going to be the absolute value of 350 hertz minus our frequency. Okay, so this means that basically F is going to be either, it's going to be plus or minus, it's going to be 350 plus or minus 7. You could do a little bit of math, find out, but pretty much either it's going to have to be 7 below 350 or 7 above 350 to have its absolute value equal 7. When you take that difference, right? So it's going to be either equal to 343 or it's going to be equal to 357. Okay, our job now is that we identified two possible frequencies, is to use this other frequency that we have and this other beat frequency that we have to identify which one of those it will be. Okay, so again, we know it's going to have 8 beats a second with the same process here. When it gets struck with 365 hertz. Okay, so this is going to mean that our frequency is 365 plus or minus 8 hertz. So this is going to be 373, or it's going to be 357. Yeah. Okay. So we need to pick one that matches both, because it needs to, in both these scenarios, we are given two, it's the same frequency in both, but we want to know which of the two options for each it's going to be, and it has to match, because it's the same frequency. And the only one that matches in both of the times when you pluck it is, or when you sound it, is 357, because that's the one that appears twice. So when you do this, you just want to figure out the two possible frequencies for each of them, and then match up the one that is the same, that appears in both of them. Here, that's 357 hertz. Okay. Suppose the threshold of hearing for a particular sound is 1 times 10 to the negative 14 watts per meter squared. How loud in decibels is a sound with intensity of 3.55 times 10 to the negative 2 watts per meter squared? We're going to use our formula, which are decibels is equal to 10 times the log base 10 of I, which is going to be our intensity, over I0, which is going to be our threshold of hearing. It's going to be, in this scenario, it's going to be 10 times log base 10, our intensity, 3.55 times 10 to the negative 2. I'm not including units, just to make it a little easier, right? And then 1 times 10 to the negative 14 is our threshold of hearing. So first, what you need to do, or what you should do to avoid making mistakes, is to take this, right? And I would recommend dividing using parentheses, because it makes it easier to ensure that you don't make mistakes. But it's going to be 3.55 times 10 to the negative 2 divided by 1 times 10 to the negative 14. So I got, this is going to be 10 times the log base 10 of 3.55 times 10 to the 12. If we now evaluate this whole logarithm, that will give us, just plug that in. I get 12.55. So 10 times 12.55, that would be 125.5. And if we round that off, that's just 126 decibels. Don't forget your units. Okay. I hope that you found this useful. And if you're taking a test tomorrow, I hope that you do well on it. And I hope that you have a good day.